This is the second lecture on rigid body dynamics. In the first lecture, we have defined a rigid body, then we have calculated its degrees of freedom, which comes out to be 6 in general, and we also proposed the problem by calculating the number of independent constants. And secondly, we have introduced the coordinate system generally used for specifying the dynamics of a rigid body. That is, we have introduced an inertial frame, which is called a space fixed frame or lap frame, and we have also introduced the body fixed frame, which is rigidly fixed with a rigid body. And we have also developed the transformation equation, which connects the space fixed frame with the body fixed frame. And we also remarked that principal axis coordinate system is a special type of body fixed frame. Today we shall discuss the general motion of a rigid body. Motion of a rigid body. The rigid body motion is generally divided into two categories. One is called a translational motion of a rigid body. One is translational motion. A rigid body is said to perform a translational motion when each and every point of the body undergoes the same displacement, same linear displacement. So if we have a rigid body over here, then say we have a body fixed frame is like this. This is body fixed frame. After some time, this same body moves over some other position without changing its shape and size, as the body is a rigid one. So this is the position, and this is the position at another instant. So this is the S prime body fixed frame, and if we found that this body fixed frame remains parallel, then we say the system is undergoing a translational motion. So the axis of the body fixed frame always remains parallel, and that does not necessarily mean that this rigid body is moving along a straight line. If the body moves along a curved point, so that the set of axes moves in this fashion without changing their orientation, then we say that the body is executing a curvilinear translational motion. And if the body moves along a straight line, this trajectory is a straight line, then we call a rectilinear translational motion. So for translational motion, this is one definition is all the points have the same linear displacement. That is, Ri is equal to P say for all i's. This is one definition. Or we may define that S prime frame, the body fixed frame, the axis of body fixed frame do not change its orientation with the passage of time. So the axis remains parallel. So this should be A. An alternative definition. B is if the trajectory of O prime, the origin of body fixed frame, the origin of body fixed frame moves along a curved line this is curvilinear translational. Otherwise the motion is rectilinear translation. Rectilinear one. This is the translational motion. The mathematical implication of translational motion is that there is another motion called the rotation. This is pure translation. That is, the body axis do not undergo any change. Only thing is that the position of O prime changes so that all the particles, this particle 1 moves from here to there, particle 2 moves from here to there, so they execute the same displacement. Now coming to the rotational motion. Rotational motion of a rigid body. A rigid body is said to undergo a rotational motion when all the particles of the rigid body undergo the same angular displacement. All the points have the same angular displacement. In this case, the axis the axis of the body fixed frame, or the axis of body fixed frame change their orientation, with the passage of time. Say we have a rigid body, it's an extended rigid body, we have two particles on it, one is here, other one is there. This is the line, and with the passage of time, these 2 points moves over there, so this point moves to there and this point moves to there, so that the angular displacement is the same. So the particle will have the same angular displacement. All the particles of the rigid body have the same angular displacement. This is the rotational motion, pure rotational motion. So delta phi, so we write delta phi is the same, and we call it, say, epsilon. Angular displacement is the same. This rotation in general takes place about an axis. So now we come to the third category, the general motion. The general motion of a rigid body. It is a combination of It is a combination of pure rotation, pure, pure translation, rotational motions. That is, if we consider a rigid body, for the sake of simplicity, say we consider a rigid body like this. It is its initial configuration. It was initially over this initial configuration, and finally let the body moves to over here. So this is the final position. This is the final position of the rigid body. The red colored one is the final configuration of the rigid body. So what do we see? This is a translation. This is the translation which takes the body from here to there, and then we perform a rotation of the axis so that the body, we obtain the final configuration of the body. So in general, in general, the motion of the rigid body can may be looked upon as the combination of these two. Now, how do we realize this? Say we fixed a particular point of a rigid body. Say this point is fixed. So we take this point from here to there. So this is the translation which takes us from here to there, and then we rotate this. We find out this position. We come to this point. Then we fix any point of the rigid body, and we rotate the rigid body about an axis passing through the fixed point. So what we do? First we take the body from here to there, and then in this dotted configuration we fix one point within the rigid body and rotate the rigid body by an angle so that a second point comes to its final configuration. Once this is done, the body is taken from one point initial configuration to the final configuration, wherein 2 points of the body has attained their final configuration. Then we, with these 2 points as fixed point, we consider an axis of rotation, and we rotate the rigid body about this axis of rotation by the right amount so that a third point, which is not collinear to the first 2, attain its final configuration. By doing this, all the points of the rigid body will come to their final configuration. So this translation is a pure translation, and the rotations that we have done in succession can be represented by a single rotation about an appropriate axis. But in order to visualize the same case, it is better to look upon the rotation in steps. Now we shall justify that the general motion of a rigid body can be decomposed into a rotation plus a translation. We shall justify that this by mathematical So this is the initial configuration, this is unprimed, and this final configuration is denoted by prime coordinates. So what we do, the initial, we take two pair of points. Consider any pair of points. Pair of points in rigid body, which is I and J. These are denoted by I and J. So the initial configuration is this particle, ith particle has position vector Ri and jth particle has position vector Rj. The final configuration, the ith particle changes to Ri prime, and the position vector of the jth particle changes to Rj prime. Now the rigidness says that Cij is equal to Ri minus Rj is equal to Ri prime minus Rj prime. This is the condition of rigid displacement, the general rigid displacement. We should prove that what happens. As we have seen that, let us consider this, look upon the situation in another way. Let in the initial configuration the body fixed frame and the leg frame were coincident. So initial configuration, in the initial configuration we describe the 2 points in unprimed frame. And final configuration, we describe the position of the same 2 points in terms of the body fixed frame. So what is the transformation relation relating to this form? Ri is a combination of xi, yi, zi, which is written as xi1, xi2, xi3. Similarly, the initial configuration is written as xj1, xj2, xj3. In general, this is written as the set of xj alpha, and this is written as a set of xi alpha, where alpha ranges from 1 to 3. So alpha is an integer less than 3 greater than 1. This is alpha. And I ranges from, and I runs over the number of particles of the rigid body. Now coming to the prime frame, these quantities are written as Ri prime, it is actually xi prime, xi prime, yi prime, zi prime, which we write as xi1 prime, xi2 prime, xi3 prime, which is written as in this rotation xi beta prime, where it is a set of where beta is less than 3 greater than 1. Similarly, Rj prime is a combination of xj beta prime. So these are the simplified notations. Now, what is Cij square? Cij square, if we write it in unprimed frame, this is basically xi minus xj whole square plus yi minus yj whole square plus zi minus zj square, which in this notation becomes summation over r alpha xi alpha xj alpha square, alpha is equal to 1 to 3. This can be written as sum over alpha. Now we recall the transformation relation that connects the transformation relation. If we recall, the transformation relation is this: xi alpha is equal to capital X alpha, which denotes the shift from S frame to SI frame, plus summation over beta A alpha beta. For I, this is I beta prime. This is the notation we used. So, if we write this is the alpha sum, and from this summation over beta A alpha beta xi beta prime, this is coming from this part, minus x alpha plus summation over beta A alpha beta xj prime beta. This is for this part. And then there is another product term of similar kind, product term. It is x alpha plus, we use another summation index, this is for this part, minus you see that these two parts cancels out, so we write it as summation over alpha, and there is a beta sum and there is gamma sum. So we have beta gamma sum. This A alpha beta and A alpha gamma are taken common. Then we left over with xi beta prime minus xj beta prime from this part, and then we have xi gamma prime minus xj gamma prime. If we could calculate in Cij in prime or final configuration, here we have written Cij in initial condition. If we could write it in final configuration, it would be xi prime minus xj prime square plus yi prime minus yj prime square plus zi minus zj prime square. So this would be some delta is equal to 1 to 3 xi delta prime minus xj delta prime square. If we equate these two relations, since both of them are equal to our Cij square, we immediately get that this relation reduces to this if we have summation of alpha a alpha beta a alpha gamma is equal to delta of alpha beta. In that case, this should be changed to some other variable, otherwise a confusion may come with the Kronecker delta function. So we see that for rigid displacement, we must have the coordinate transformation must satisfy this relation. In the coordinate transformation, this is the same for all the particles. We have assumed this to be same for all the particles, so it is the translation part. And the next part, which is different for different particles, is taken care of by this part of the translation, which is characterized by a 3 by 3 matrix whose components are alpha beta, where alpha beta ranges from 1 to 3. And we see that this is the property that should be obeyed by the components of the matrix for the rigidness of the displacements. So we know this is an orthogonal matrix. This is an orthogonal matrix, or rather these A alpha beta are the components of an orthogonal matrix which designates the rotation. So if we want to represent any rotation, the process of rotation is represented by an orthogonal matrix such that the length of the vector does not undergo any change due to this orthogonal transformation. So in this treatment we have shown that the general motion of a rigid body can be looked upon as a combination of pure rotation, pure translation plus a rotation. And the rotational motion is characterized by an orthogonal transformation, and we have deduced this in a reverse way. That is, we have shown that to retain the rigidness of the displacement, the coefficients of transformation must satisfy the property of orthogonal matrix, and as an orthogonal matrix is one which represents the rotation. So the general motion of a rigid body is a combination of rotation and translation, which is known as either Church's theorem or as the Euler's theorem. So this is one important part of rigid body dynamics. That's all for today's lecture. We shall come with further discussion on rigid body in the next class.